Okay. Today we're going to talk about a different kind of Fourier transform. Actually, the most classical kind of discrete Fourier transform, not the Boolean one, but the one over, well, Zn. So this is the notation for the integers mod n. So let me recap what we did in the last couple of classes, and also, opposite of recap, tell you what we're going to do in the next few classes. So 2 lectures ago, we really dove into the Sethapakdi Fourier transform, sort of the Boolean Fourier transform, which I've written here as like the Fourier transform over, this is the vector space, if you will, the n-dimensional vector space over the field with 2 elements, the integers mod 2. Or another way to think about it, it's just, you know, the Boolean strings where somehow the operation, or you consider the operation of adding 2 strings mod 2, or XORing 2 strings. Okay, and that was all about decomposing any old Boolean function, mapping, let's say, the Boolean strings into complex numbers, into, you know, these particular basis functions, the XOR functions, XORs of subset functions, and trying to figure out, you know, like what strength each XOR function has in this given function g. More precisely, in linear algebra terms, writing g as a linear combination of these functions. And we introduced this notation, ket g, for the vector version, which is usually a quantum state of a function g. And this Fourier transform kind of was about expressing g as, these are the linear combinations, these coefficients are the numbers, the strengths of each of these pattern functions chi-s. Okay, and then in the next lecture, Simon's algorithm, we put this to good use. We knew there's like a very simple quantum circuit that does this Fourier transform. You just have to put a Hadamard gate on each wire. And we solved this problem, Simon's problem, which was the following. You're given like a function f. Well, you have a function f mapping the Boolean cube into some set, which I called colors. And it had the property that it was periodic for some period L. This is a Boolean string L. And that meant that like f of x was always equal, sorry, this should say for all x. F of x is always equal to f of x plus L. And this is, you know, this addition mod 2 or XORing operation. So these pairs were always had the same color. And then also, I didn't write it here, but like all the different other pairs, different pairs have different colors. And so you imagine that there is such an L periodic function f, and you're given a quantum circuit that implements it. And Simon's algorithm actually determines what that period L is with only something like little n uses of the circuit computing f, or implementing f. That's pretty cool because classically you would need something like square root of 2 to the n uses of a circuit that could only accept classical inputs. So actually in today's lecture and the next lecture, we're going to do it all again. Like literally do it all again, except with the Fourier transform over a different domain. We're going to think of like the inputs not as, you know, bit strings that can be XORed together, but as just integers that can be added and also multiplied together. Okay, so I can maybe do this by some judicious erasing. So today, we're going to talk about the Fourier transform over the integers modulo capital N. Okay, and you should think of capital N again as like 2 to the little n, where little n is like a physical reasonable sized number, like 1,000, and so capital N is some unphysically large number. And again, this is all going to be about decomposing any old function, which we'll now think of being mapping the integers mod n into complex numbers. Or you can think of g as like just a vector of complex numbers of length capital N, but we think of the coordinates of the vectors being indexed by integers between 0 and n minus 1, rather than by Boolean strings. Okay, into linear combinations of some new kind of pattern functions, not Boolean functions, but some other kind of pattern functions. And in fact, I'm going to abuse notation and also again call them chi. It's maybe a little bit confusing. I'll make it slightly better by like writing capital S and capital X here, but since in my font those look the same, it's basically going to be impossible to tell. But well, you'll catch on. So we're going to be decomposing these g's into sort of, you know, their linear combinations or like strengths of various, well, they're going to be sort of like discrete sine and cosine functions, although we won't stress this too much, but there will be some angles involved. So these are going to be some functions, chi 0, chi 1, up to chi n minus 1. And again, these functions are actually going to be indexed by the integers between 0 and n. These will be particular of these pattern functions that map the integers mod n into, say, complex numbers. And these will be a different set of orthonormal vectors, if you think of these as vectors, in capital N dimensions. And in fact, I'll tell you what they are now, but just so it doesn't seem like a complete mystery, but we'll explain them more carefully later. But I'll tell you, chi sub capital S at x, this is an index, that's an S somehow, into this list of pattern functions chi. That's an input. It's also an integer between 0 and n, is omega to the s times x, where omega n is this primitive nth root of unity, which I hope you're used to by now. And this is just like multiplying these two numbers together, like as integers. This kind of has a similar formula, actually. Some root of unity to the power of s times x. Good. And so this is the classic Fourier transform that's usually used to detect kind of periodicity patterns in vectors. Talk about this more in this class and next class. But what's crucial about it in the setting of quantum, which was just like what was crucial about the Hadamard or Boolean Fourier transform, is that you can compute it efficiently with a quantum circuit. So in n, capital N is a power of 2. This Fourier transform which now maps a vector of data into a decomposition of like the strength of this chi s in the data, that's g hat s, times the index ket. This Fourier transform can be computed efficiently by a quantum circuit. Namely with, well, today we'll see basically little n squared 1 and 2-bit gates. Okay, so if n is like, little n is like 1,000, then this is fine. This is like maybe 1,000,000 gates. Hopefully we'll build a quantum computer that has 1,000,000 gates. But 2 to the 1,000 is like an unphysically large number. So like there's something amazing going on. You're doing this like pattern decomposition Fourier transform thing on like lists of data with 2 to the 1,000 numbers. Yeah?
Wasn't this the basis for the fast multiplication algorithm you showed us in week 1 in the homeworks? And so can classical computers not do this efficiently?
Classical computers can do this. This is like basically a matrix multiply. They can do it in time capital N squared steps. Because it's capital N by N, capital N matrix. So to multiply that by a capital N vector, you can do that in capital N squared steps. In fact, what's so awesome about this discrete Fourier transform, not only is it very useful, but you can actually, even better, do it in around n steps. Well, more precisely, n log n steps. And that's why it's super useful and great in life. And that's fast if, like, greatest capital N is like 1 billion, but like now we're imagining capital N is like 2 to the power of 1 billion. Or 2 to the power of 1,000 or something like that. In fact, as I'll show you later, you can even do better than this. You can compute this Fourier transform quantumly to, let's say, very high accuracy, high enough accuracy for all the applications that you'll need, with a number of gates that's more like n. It's again actually like n times log n. That's even better. And this one is usually called the quantum Fourier transform. But there are many kinds of quantum Fourier transforms, actually. This is the most famous one. Great, so that's what we're going to talk about today. And then, like next lecture, will like literally repeat Simon's algorithm in this context. And it'll be very similar. You'll have like an unknown, well, you have a function that maps the integers between 0 and n into some set, whatever, we'll call it colors. And it'll be L periodic. And now this will really have the flavor of being periodic. This will mean that like f of x equals f of x plus L equals f of x plus 2L equals etc. for all x. Okay, actually for this to make, this addition is always mod n. So for this to make sense, L should divide into capital N. I know, I'll come to that in a second. And then, like, literally by repeating Simon's algorithm almost, we'll show that with, like, I don't know, something like 3, it's even better, uses of a quantum circuit implementing this f, you can find L with high probability. And you would then like to say, like, oh, but a classical algorithm could not do this very efficiently. But actually, a classical algorithm can do this efficiently for a very stupid reason, which is probably what you were umming about, which is that, well, if capital N is like a power of 2, like I said, this is a stupid reason, but then like, the only numbers that divide 2 to the n are the powers of 2. And the only possibilities are like, 1, 2, 4, 8, 16, up to 2 to the little n. So there are only little n different possible L's. So a classical one can just try them, basically. Just pick an x and a candidate L and see if this holds. So a classical algorithm could also do this pretty efficiently with like around little n uses. Well, still it's good, but it's a little weird. So actually, what we'll subsequently see is that you can still do Simon's algorithm pretty much as written, even if L doesn't literally divide capital N. So later, we'll see that basically this Simon thing still works as long as L, okay, first of all, maybe it shouldn't be too close to capital N, but maybe it's less than root n, it's still some enormous number, doesn't literally divide n. But like maybe there's like a little bit of fudging in the function capital F at the end. So like, here's like the numbers between 0 and n minus 1. And like maybe here the function looks like this. It's like periodic. This is L. And then, oh, like it can't quite wrap around. So like, okay, it's a little bit wrong there. Well, with Simon's algorithm, you can still find L. Okay? And then if, in that case, it's much harder for an algorithm classically, because for a classical algorithm, now this capital L can basically be any number, potentially between 1 and, let's say, root capital N. This is like 1.4 to the little n. And it's like exponentially hard for a classical algorithm to solve this problem. So we'll see that. That's just like annoying. It's some like annoying math to check that that is going to work. And then later, we'll see Shor's algorithm, which exactly uses this, applies this algorithm to kind of numerical looking functions. Functions like this, f of x equals a to the power of x mod m, where a will be some number the algorithm itself picks at random, and m will be a number that the algorithm is trying to factor. And then you can compute this classically efficiently, so you can make your own quantum circuit that implements this function. And it will be basically periodic with some period L. And due to some like known number theory tricks from the 1970s, if you could find that L, you could find the prime factors of capital M. And so then you can find that L with the quantum computer, and you can therefore factorize numbers M. So that's what we'll see. Actually, let me make a small comment. first of all, you can perfectly well define this Fourier transform for capital N, which is not a power of 2. And we'll work with that. We'll do that for most of the lecture. But then when it comes to actually implement it, right, I mean, you have this like domain, which is the integers mod capital N. Okay, you store numbers on a computer in binary and base 2, and it's like very convenient if capital N is a power of 2, because then every little n-bit string corresponds to a number. In fact, it's known that you can efficiently compute the discrete Fourier transform with a quantum computer, even when capital N is not a power of 2. It's just this like severe pain to take care of everything, so we will not talk about that. Okay. And let me make one more comment, which is that in future lectures, we'll see a generalization of this like story that happened last week and is happening this week, where we define a Fourier transform and then consider like a notion of a periodic function on it, and we use a quantum computer to find the secret period. There's a generalization where your domain, instead of being, the f2 to the n, the bit strings with the XOR operation, or Zn, the integers mod n with addition, it will be any group. It's a mathematical notion, an abstract algebra notion. And you'll have a Fourier transform for that group. And like you'll have, instead of an L periodic function, like an H periodic function where H is a subgroup. And well, we'll see all those mathematical charms later in this course. OK, any questions? Great. All right, so we are going to dive into this. It's going to be some math talk for a while. OK, so let's see. Yeah. So now we're going to imagine that maybe I shouldn't have erased this, we're studying functions whose domain is the integers from 0 to n, or we're like vectors of data where the indexing is just the integers 0 through n. Like this thing I erased where like f of x was like a number a to the power of x. Okay, well, there we think of a and x as like numbers mod n or m. Okay, so we're going to again, just to remind you a little bit, associate a function that we care about, little g, mapping the integers mod n into, let's say, complex numbers, to a vector, which is, again, basically just the truth table of this function, or just a list of all its values. G0, G1, okay, all the way down to G capital N minus 1. Okay, this is in C to the capital N. And we're going to do this trick. I mean, I always feel ashamed when I talk about this, but we're going to build one of a root n normalization into it to make it convenient. Okay, so we're interchangeably can think of it like a vector of data as a function on the integers. And one could also write this like this, 1 over root n with Bra-Ket notation, sum, x goes from 0 to n minus 1 of g of x times ket x. Okay. As always, ket x just stands for the elementary 0, 1 vector that has a 1 in the xth coordinate. And this is often, or we're going to set it up so that this is a quantum state, usually. This is a quantum state if the sum of the squares of the magnitudes of the amplitudes is 1. So if and only if, well, we've been writing it like this. The average over all x between 0 and n minus 1 of magnitude of g of x squared is 1. Okay, so we'll usually normalize our functions g, so this holds, and that way we can think of them as a quantum state and potentially load them into the actual quantum state of little n many qubits. Okay, and good. So we're going to cook up now. I'll tell you again about these capital N many pattern functions that the discrete Fourier transform cares about. And when we introduced the previous Fourier transform, the Hadamard one, I talked about it in a bit of a level of generality because I knew we were going to come to this point. you kind of have like a Fourier transform whenever you just have an orthonormal basis in Cn. To any orthonormal basis in Cn, you can kind of think of it as a Fourier transform, which just rewrites your data vector in this basis, figures out its coefficients in this alternate interesting basis. So you're just always like cooking up like quote unquote interesting like orthonormal bases that you would care about. So that's the point. These are going to be these functions, when thought of as vectors in this sense, are going to make an orthonormal basis. Oops. Okay. And then you can make a matrix out of them by just stacking them as columns. Okay, and whenever you have a matrix with orthonormal columns, it's a unitary matrix. So this is an n by n unitary matrix, which is kind of convenient because this is exactly the sort of transformation which you can affect with a quantum computer or by the laws of quantum mechanics. And what is this transformation? This is a transformation that moves, the first standard basis vector here, and the second standard basis vector here, and the last standard basis vector here. So it's the transformation that takes the standard basis and moves vectors to the interesting chi basis. For the actual Fourier transform, you kind of want to do the reverse. You want to like take a vector and like think of it as sitting in the new basis, the chi basis, and like bring it back to the standard basis to figure out what the coefficients are. So this is actually going to be technically the inverse of the discrete Fourier transform that we care about. But I'm not going to lie to you. Like when I was preparing this lecture, like 20 times I like confused myself about which way is the inverse and which way is the forward. And like it basically doesn't matter because like in the Hadamard transform case, they were literally the same matrix. It was a symmetric matrix. And here, the matrix and its inverse, in other words, its transpose, are like basically the same matrix. So like it hardly matters if you remember which way is the inverse and which way is the forward direction. But I'll try to get it right. Good. So the Fourier transform, the inverse of this matrix, which is what you get if you just put these chi's as rows and complex conjugate them, that will be the operation that like takes a data vector G, and when you apply the Fourier transform to it, gives you a new vector with all the strengths, all the G hat S's. Okay, any questions? So now I already spoiled it for you. I like told you the formula for these chi's that will form the pattern functions for this kind of Fourier transform. But I'll just spend a little bit of time telling you kind of where they come from. So, and it even has a little bit to do with group theory, like I mentioned. So let's look at the one set of pattern functions we had before, the XOR functions. They had a very cool feature, which is kind of like the signature feature of what goes on in Fourier analysis or harmonic analysis. These XOR functions. Remember, these were the functions. Now, chi s, think of this as a bit string applied to another bit string. It was -1 to the s dot x. But now this was like the dot product, in f2 to the n. The cool feature that these functions had was the following. I'll write it and then put it in a box. If you apply it to x plus y, you get chi s x times chi s y. Okay, and just to emphasize, like this is the XOR operation, or it's the way you add mod 2 n-bit vectors. And this is like just regular old multiplication of real numbers. And Well, first let me just show you why that's true. We never really use this feature of these XOR functions explicitly. But anyway, just by definition, this is -1 to the s dot product x plus y. And the dot product is linear, so this is -1 to the s dot x plus s dot y. This is still mod 2 in the power, but if you're raising -1 to something, it really only matters if it's even or odd. So then this is -1 to the s dot x times -1 to the s dot y, and that's this. Okay, so this in math and algebra, like this, such a function chi is called the character of the group because somehow it converts the addition operation here into like multiplication. Well, anyway, if you're not that into abstract algebra, you don't have to worry about it. But this is like the cool feature, the characteristic feature of harmonic analysis.
You know the etymology?
What's that?
You know the etymology of character?
Is it like revealing the character of?
Okay.
I don't know. Oh, it was like I thought you were gonna tell me.
No, I have no idea.
Oh no, it's probably etymology. Yeah, I mean, I think there's like representations, right? And then like I think this is like a character, like a particular character of the representation that like identifies it. I don't know. I mean, I know that's why we're writing chi, right? Because it's the first letter in like character in Greek or whatever.
But then why is it through an normalization?
You'll see. We'll actually use this today when we're constructing these new character functions. But anyway, mathematically, it's like the definition of what is a character of a group.
Yeah, sure. But like, it's just like, why do we want vector that satisfy this?
Yeah, I don't have like a one-word explanation which will satisfy you. Although we will use this property when we somehow decide to, on particular these chi functions and check that they're orthonormal. Okay, so we're just, for whatever reason, let's just say we want the same thing for, functions, but now where we think of the domain as integers mod capital N. So let's just, basically this will force the answer on us, as it turns out. Just deciding that you want this box property will force the answer, what these chi's are. So, okay, one thing is I'll just apply this box rule a few times and see what happens. So, well, you need that like chi of any s of x plus 0 should be chi s of x times chi s of 0. But okay, plus 0, that's just chi s of x. And okay, now we have an equation. We could just cancel these out. Unless there's 0 for every choice of s and x, but that's like an undesirable
No, it's not for
case.
every. It's like for this particular s.
Okay, for this particular s, if there exists an x for which this is non-zero, then you can make the deduction that I'm about to make.
So you could have one like complete zero chi s.
Yeah, you can have a character. I suppose according to this box, the 0 function would be fine.
Yeah.
But we're going to disregard the 0 function. We don't want it. It's not going to be orthonormal. Okay, so what that implies, I mean, just canceling it, is that chi s of 0 is going to be 1 for all s. So whatever these capital N functions chi s are, they're going to have the property that if you plug in 0, you get 1. Okay, that's fine. Now let me show another little move. Also, if I do chi s of x plus x plus x, I mean, you can, by induction, extend this out. If you like add up 3 things here, you'll get the product of the 3 things here. So I'm going to do that actually capital N times. Then you get chi s x times chi s x, also n times. Okay, also known as chi s x to the power of n. This is just like a regular old number now. And then this is n times x, but this addition is always happening mod n. So this is actually 0 mod n. I mean, if I take capital N times capital X mod n, I get 0. And so this is chi-s of 0, which we know is 1. Okay, so we deduce a new fact. Whatever this number chi-s of x is, it better have the property that its nth power is 1. In other words, all the values chi-s of x have to be nth roots of unity. And just as a little aside, like this is like the point in the entire course where like we're forced basically to talk about complex numbers. I mean, if it weren't for this, I would just at the beginning of the course be like, doesn't matter what the laws of nature say, like let's just have all our amplitudes be real forever. And as you saw in homework, you can actually do that for the purpose of quantum computation without loss of generality, only work with quantum states that have real amplitudes. But occasionally it's convenient to have complex amplitudes, and like we're going to do it precisely because of this one spot. Okay? Good. So now we kind of know that these functions chi, which we're somehow seeking, are going to be roots of unity, nth roots of unity. So hopefully you remember all your complex number stuff, but very briefly I'll draw you a little picture. Now, again, for the first time, this two-dimensional picture will be representing one complex number, not two real numbers. It's the real axis, the imaginary axis, right? This circle is like all the complex numbers of magnitude 1. And if we're interested in capital nth roots of unity, there's our particular favorite one, which is this one, where the angle here is 360 degrees divided by capital N. And we usually call this omega sub n. It's called like the primitive. This just signifies that it's like the first one, nth root of unity. And, well, it's this. It's the unit vector that's rotated by this amount. So it's e to the 2 pi I over capital N, or if you like, cos 2 pi over capital N plus I sine 2 pi over N. And as you know, the other nth roots of unity are the powers of this character, or I shouldn't say character, guy. Omega n squared and omega n cubed, and omega n to the 4th. I guess I'm drawing the picture where capital N is 16. Okay, and then they go around all the way up to this one's omega n to the n minus 1. This one's omega n to the n, aka omega n to the 0, aka 1. Okay. Hopefully you remember this stuff. Yeah?
I think Alex has this before, but it shouldn't be clear why we need this feature in our algorithm yet, right?
No, I just, for some reason, I decided to, like, instead of just saying, like, well, here are the chi-s functions, read them and weep, like, this is the Fourier transform that we're going to care about, and explain why they're orthogonal vectors, the columns, or these functions. I thought I'd kind of like, develop them, and somehow they, basically, if you write, it turns out, let's just say that if you like write this like sort of fact for any group, then you kind of come to develop like the appropriate pattern functions chi-s for like that group. So I didn't motivate like why did it really we started with this thing, but like if you take this as like a fact, then you'll discover these functions. Good. So I mean, after a while, like once I tell you these functions, you can forget all this stuff and just be like, well, these are the functions or the vectors that you use in the discrete Fourier transform. Yep.
Notation question.
Yep.
Are those supposed to be capital X's, and does that mean something separate from these X?
Oh yeah, good question. For whatever reason, I thought it would be like kind of confusing that I was using like chi sub s for both the old XOR functions and like these new functions. But on the other hand, like I wanted to use the same symbol chi because it's supposed to be like a character. So I was like, how can I distinguish them? I was like, well, I'll write like capital S and capital X to stand for numbers, mod capital N, and little s and little x to stand for strings. That's like, no, it makes no sense, but that's what I decided on. And it's also particularly bad, right? Because in my font, like little s and capital S and little x and capital X look the same, just enlarged. But anyway, for the rest of the class, most of the rest of the class, we're not going to talk about bit strings anymore. And capital S and capital X will be integers between 0 and n, integers mod n. Yeah, thanks. Good. So, all right, let me just make a long story short. Like now that we know, like these things have to be powers of or roots of unity, you can use this fact to see that, like, chi s of 2 times x has to be like the square of chi s of x, and chi s of 3 times x has to be like the cube of chi s x. And long story short, you have like one character for each of these roots of unity. So let me just redefine them now. So here they are again for 0 between s and n. You have one for every integer between 0 and n. We have this function, chi s of x is primitive nth root of unity to the power of s times x. Or maybe you can think of it as like x times s. It's the same. So in particular, like, let me put it back to s times x. Particular, like, chi 7 of x is omega n to the 7x. Okay, so like chi 7 of 1 is omega to the 7. Chi s of 2 is omega to the 14. Chi s of 3 is omega to the 21, and so forth. So they're a little bit hard to plot because their values are complex numbers. And it's like hard to draw like a plot where like the range is complex numbers. I'll try to draw one anyway, though. So I'll plot like the real part of chi s of x. So in the horizontal axis, it'll be Zn. So x will be in Zn. So it goes 0, 1, 2, 3, all up to n minus 1. And actually, let's see. The first one, chi 0 of x, this is just constantly 1. Right? If x is 0, then it doesn't matter. Sorry, if s is 0, it doesn't matter what x is. This power is always 1. So, well, the real part of the chi s of x is the same as the actual value. So, like, this is the function which is everywhere 1. And then chi 1 of x is the function that just it's omega to the x. So its values at 0, 1, 2, 3, 4 just go around the circle. So again, it's a complex number. It's hard to plot. If you just plot the real part, though, then the real part is the horizontal distance. So it looks like a cosine wave. That's chi 1 of x. And chi 2 of x is like omega squared to the power of x. Right? So chi 2 of x gives you like the powers of omega squared. So like that's the first value, second value, the third value. So as you go x from 0 to n minus 1, it wraps around the circle twice. And so it looks like, hopefully I can draw this, like a cosine wave that's like half as narrow. Anyway, that's somehow chi 2 of x. OK, so the real parts look like these discrete cosines, and the complex parts look like discrete sines. But actually, we're not going to really talk much about sines and cosines. The main thing is that these things are periodic, kind of. This chi 2 is like repeats every half, and chi 3 repeats like every third chunk. Yeah.
This particular ordering was not forced by our wish list. Is that correct?
No. Yeah. Well, basically the characters are actually in one-to-one correspondence with the roots of unity.
Yeah, but
so
you
then
can
it's
start with whatever realization you want.
Yeah, that's
It
true.
sounds just convenient.
Yeah, I mean it's natural to order them as like this is the 0th, this is the 1st, this is the 2nd, this is the 3rd. Yeah.
Making sure it wasn't false.
Yep. Yeah, I mean, really, an orthonormal basis does not have inherently an order, but, well, once you want to write down vectors, it's convenient to order them. OK, so let's collect up some facts about these functions, or you can think of them as vectors if you list them in a long list. OK, as I said, first of all, the 0 character is constantly 1. And actually, this was a feature of the XOR functions too, right? The the XOR function where you take the XOR of like none of the bits is like constantly, well, in truth table value, it's constantly 0, but -1 to that is constantly 1. So that was a feature before. And actually, that was the feature that like gave us the property that if you like took all zeros and plugged it into the Hadamard transform, you got the uniform superposition. So actually, that'll be the same in this case. But we'll usually cook up the uniform superposition by using the Hadamard transform because it's super easy. But it would be the same here. OK, here's another minor fact. Now that we're finally grappling with complex numbers, we have to remember about all these like complex conjugations that sometimes happen. So the complex conjugate of this number, chi s x, well, OK, it's the complex conjugate of omega n s times x. I mean, the complex conjugate like reflects downwards, and right. So this one goes to this one, and this one goes to this one. So you can see it's just omega n to the minus s dot x, which is chi minus s x. OK, that's like a minor fact that we'll occasionally use. It just says like if you take the complex conjugate of a character, you get like a different character, which is good because sometimes you take complex conjugates. Right, this is another like wacky fact, but this is also the case with the Boolean Fourier transform. I mean, this is the definition. Multiplication is commutative, so I could reverse these. So that tells us that chi s of x is actually the same as chi x of s. Now, usually we try not to like mix, even though like the domain of these functions is like 0 through n minus 1, and like the index set is also 0 through n minus 1. That's like sort of a coincidence, and like it's a little bit better to like keep them as like separate type objects in your head. But we will use this fact once when we like discover what is the transpose of the Fourier transform matrix. OK. And now I come to the key fact. Like the whole raison d'etre of these functions is that they're orthonormal. Or if you stack them into vectors, these vectors are orthonormal. OK, this is what you really need for it to be a Fourier transform to make sense of this statement. I'll take my data vector and write it in this new orthonormal basis and find out what are the strengths of each of these chi's in my data vector. Good. So actually, one way you can prove this is like in the end of the class, as I told you, I'm going to tell you how to build the Fourier transform as a quantum circuit. And quantum circuits can only create unitary matrices. And the Fourier transform is just the matrix that has these guys as its columns. Well, that's actually the conjugate transpose, but same difference, basically. And therefore, that's like going to be like an indirect proof that this is a unitary matrix. But anyway, I'll just directly prove first that these are orthonormal vectors or functions. And it's a pretty easy proof based on all the properties that we've seen. So what are we trying to check? We're just trying to check that this quantum state, let's say chi t, well, actually, we don't know yet that it's unit. So we don't know it's a quantum state. It is going to be unit, though. Just that this vector is, that this is 0. This inner product is 0 if t differs from s. So they're perpendicular if t and s are different. And it's 1 if t equals s. In other words, it's a unit vector if they're the same. OK, so by definition, this is the average. So x goes from 0 to n minus 1 of now you got to remember when you do complex numbers, inner product, you have to put in a conjugation. So it's chi tx complex conjugate times chi sx. Okay. And now we'll use this fact. So this is average over x of chi minus tx times chi sx. Okay, now we'll use, oh, it's no longer here. Well, this key fact. Oh, actually, we have to do it in 2 steps, I suppose. We can use this fact. Say this is chi x minus t. This is chi x s. Okay, then the key fact says this is equal to chi x s minus t. Right, this is the character property. And then I'll like undo this little reversal. This is chi s minus t x. So, all right, this is just some like playing around arithmetic-wise. Okay, so what we've seen so far is that the inner product of chi t and chi s is average. X goes from 0 to n minus 1 of chi s minus t x. Okay, so now if s equals t, so we're looking at the inner product between the character and itself, then this is 0. And then chi 0 of x is constantly 1. So you're averaging constantly 1. So it's just 1. Okay, and that's good. So that says that these are actually unit vectors, and therefore also quantum states. And what about if they're different? Okay, so say r equals s minus t is not equal to 0. Then what are we doing? We're getting average over x of chi r of x. Okay, so chi r of x, it's like, well, this thing is omega n to the r times x. So as you're varying x, you're getting powers of omega to the r. So if this is omega to the r, like r is 3, you're getting the average of this vector, that's the 0th power, the first power of omega cubed, the second power of omega cubed, the third power of omega cubed, the fourth power, and it goes all the way around. And like the center of gravity of these vectors is 0 by symmetry. I think you also did on this on your homework. I mean, you computed that the sum or the average of, omega to r times j or r times x as x runs from 0 to n minus 1 is 0. You can also do it by using the formula for a sum of a geometric series. So I'll assume you did that homework or that you got that picture from the symmetry. This is 0, which is what we want it to be. That says that these guys are perpendicular. Okay. Great. So now we have orthonormal vectors or orthonormal functions. We can have a genuine Fourier transform from them. And so we know that this matrix is indeed unitary. And as I said, this is the matrix, right, that like maps the standard basis to the chi basis. And therefore, it's actually the reverse of the Fourier transform, as I tried to explain before. So this is actually the inverse discrete Fourier transform. And the inverse of this, which is also its dagger, right? Its conjugate transpose, is the thing that maps the chi basis to the standard basis. Okay, and this is the thing that's called the discrete Fourier transform with respect to capital N. Okay, And so I guess the inverse matrix of this, or the conjugate transpose, it's the thing that, the DFT, it takes a data vector G, maps it into sort of the list of strengths of these chi functions as patterns in the data G. Okay? And this G hat S is just the coefficient of G when you put it into this new basis. Okay, which is the average over X of chi S X star G of X. And let me just write it out so you get the point. So when capital N is 4, then we have a 4 by 4 matrix. And this inverse Fourier transform it's 4 by 4, and it has a 1 over root 4 out here, and omega is omega sub 4, the 4th root of unity, which is actually I. And the matrix looks like omega to the 0, omega to the 0, omega to the 0, omega to the 0. So those are all 1s, actually. Omega to the 0, omega to the 1, omega squared, omega cubed. These are the multiples of 1. Omega 0, omega 2, omega to the 4, omega 6. These are the multiples of 2. Omega 0, omega cubed, omega 6, and omega 9. These are the multiples of 3. So that's literally the matrix. We just proved it's a unitary matrix. You can also reduce the exponents mod 4, because this is the 4th root of unity, so omega to the 4 is just 1. Yeah?
Do we want the dagger of this?
Yeah, this is the inverse discrete Fourier transform. So the discrete Fourier transform is the dagger of this. And what happens if you dagger this? You transpose the matrix, which actually does nothing, right? That's because, what is the formula here? It's omega to the s dot x, where I'm not sure which one's s and which one's x. Maybe this is s and this is x. So switching rows and columns is like switching x and s that does nothing. But then it's complex numbers, so you have to do the complex conjugate. And that basically means negating things. So if you put negatives everywhere, then that's the discrete Fourier transform. Okay, so the discrete Fourier transform is the matrix that looks like this, where the s comma x entry is this, well, times 1 over root capital N. Okay, and if you see, go to Wikipedia or whatever, you'll see long encomiums to the glory of this matrix. And just as a little bit of a hint or a reminder of what's coming up, not a reminder, a hint, basically we're really only going to use one fact about this Fourier transform, which is that, let's say you have a signal or a function or a data vector that you care about, capital N, which is periodic. These are the values. For some reason, I'm drawing it as a spike function. It's periodic with period L. Then the Fourier transform, this is the x-axis. The Fourier transform, this will be the s-axis now. Suppose this is g hat. It will be periodic with period capital N over L. And actually, no matter how this is translated, it'll always start at 0 here. But it's a bit of a funny plot, because these will actually be complex numbers, but it'll be the same complex number, which I just drew with some arbitrary height on the board. And this is the main thing we'll use about the discrete Fourier transform. OK, questions? All right, so there's this glorious Fourier transform that tells you if you give it like a periodic data vector g or a periodic function g, the Fourier transform kind of reveals the periodicity in some way, in the same sense that our old Boolean Fourier transform kind of revealed XOR patterns. This Fourier transform kind of reveals periodicity in data indexed between 0 and n. And now I got to tell you that the quantum computer can efficiently do this transformation. So that's the last 25 minutes of this class. We'll be like drawing some quantum circuit diagrams. And it's a little bit fun. It's a little bit annoying. We'll do. We can call it both of those things. This is what we're going to do. We're going to implement this matrix. It's a capital N by N matrix. And we're going to use n times n plus 1 over 2, which is less than n squared, 1 and 2 qubit quantum gates. And I'm going to kind of do it by example, because there's a lot of notation otherwise. So I'm going to do it by example. I'm going to make it a more complicated example. Now little n is going to be 4, and therefore big N will be 16. OK, so what are we trying to implement? Trying to implement the transformation that takes cat x, and this is like a number between 0 and 15, but like encoded by 4 bits. OK, so it's like a 4 qubit state. And it's supposed to output this state, 1 over root 16. Sum s goes from 0 to 15 of chi s x star ket s. OK? So this is some other like 4 qubit state, because s is also represented by 4 bits. And like just trying to get like these funny amplitudes onto each of the 16 kets. And like the amplitudes depend on both x and s, like in that matrix. OK, and what are these amplitudes? Well, since this is the Fourier transform, we've got the star in there. So this is actually omega, the 16th root of unity to the power of minus s times x. And this is like the normal multiplication of two numbers between 0 and 15. And I'm going to call just notation from now on. I'm going to write omega bar for omega 16 to the minus 1. OK, so this was like omega 16, the primitive 16th root of unity. And like this symmetric one is omega bar. OK? And so this, I just do that so that this will just be omega bar to the s times x. OK? OK, and if you want to be really explicit, right, this is e to the minus 2 pi I over 16. OK, so how to do this? So let me write this even more brutally explicitly. Okay, so we need a circuit that for each number, it implements the 16 of x equals, OK, so 1/4 times. Well, it's going to be some amplitude on 0, 0, 0, 0. That's capital S equals 0. But omega bar to the 0 times x is 1 for every x. That's 1. And then what do we get on 0, 0, 0, 1? That's when s equals 1. We need to get omega bar to the x. OK, and then we need to get omega bar to the 2x onto s equals 2. And then we need to get, et cetera. We need to get omega bar to the 15x onto that ket. Okay, so we need to build a circuit that does this. Okay. Now here is like one cool thing, which is that this, I'm going to erase this now. That's an unentangled state. 4 qubits. It's one of the surprises. Maybe it does not look unentangled, but it's unentangled. And I'll demonstrate that to you. Because it's this guy. It's 0 plus omega bar to the 8, 1 over root 2. Tensor 0 plus omega bar to the 4, 1 over root 2. Tensor 0 plus omega bar squared over root 2. I claim that this equals this.
This state does not depend on x.
Oh, yeah, wait.
8x.
Yeah, thank you. That's critical. Right. So do we see this claim? Like the root 2's like, match up. That gives you the 4. And then like what if you expand this, right? Like this is the most significant bit, kind of. This is the second most significant bit, third most significant bit, least significant bit. So like basically, yeah, like what do you get when you expand this on like 0, 0, 1, 0? Well, you get like the 0, so you get nothing. You get the 0, you get nothing. Here you have a 1, so you pick up the 2. And here you get nothing, so you get 2x. Or what do you get on 1, 1, 1, 1? Well, you pick up the 8x, the 4x, the 2x, and the x. So you get 15x. Okay.
It's like so much of coincidence. I don't know. Like you use so many facts. Like
Well,
you
how
use the
awesome is
fact
it?
that coefficients are periodic, and you use the same fact that like the qubits in binary are also kind of like could be expanded because of this. Like this, I don't know.
Yeah, how awesome is that? Yeah. I mean, it's a glorious topic. Well, all I can say is, I didn't say this, but here's like a rule of thumb or like a life pro tip. In quantum computing, let's say you have like a giant capital N by capital N unitary matrix, but like it's got like somehow like a very simple explanation, like a very simple formula. Like this matrix has like an incredibly simple formula. Like you can write down, the SX entry is like omega to the S times X. Usually in those circumstances, there's an efficient quantum circuit that computes the unitary, if it really has like such a simple formula for the entries. So because this guy has such a simple formula for the entries, like that's why like maybe you should believe that it's going to be possible to compute it efficiently. But it is true that like it just becomes like incredibly extra nice, like when capital N is a power of 2, and it's it's great.
But it does work out nicely.
No.
Yeah, like you see, it's not even computing efficiently. Like this is like this state is unentangled. Like it's even more, right?
Yeah. That also happened in the Boolean case, right? Like the Boolean case, what did you do? Whatever x was, you just like stuck a Hadamard on each gate. So like there, it's like super clear that it's unentangled.
Yeah.
Because like you can even prepare the qubit separately. You're not going to be able to do this here because like this third output qubit still depends on the 4 input bits x. And this one like still depends on the 4 input bits capital X. Or does it? Think about it. But like this formula really is similar to like, the Boolean Fourier transform where like basically in the Boolean Fourier transform, like this was just -1 to the x0, -1 to the x1, -1 to the x2, -1 to the x3. It was like unentangled pluses and minuses. Okay, so now I will try to draw the circuit. Okay, so it's got, in our case, 4 input qubits or wires. Okay, and I'm going to think of like x as kind of like this. Okay, so this is like the least significant bit of the integer x. This is the most significant bit of the integer x. And then we need to get like the s's out. And here's a little trick. It turns out it's more convenient to compute this output in the reverse order, to like get this onto the top wire. No, wait a minute. To get this onto the top wire, this onto the next wire, this onto the next wire, this onto the next wire. That is the reverse order. So I mean, this is like somehow like the most significant bit of s. Okay, so this is what we're going to accomplish. Maybe it's not exactly clear what I'm talking about now. You're getting a little confused, but this is what we're going to accomplish. Right, because this is like the least significant bit of x. Anyway. So the actual qubits are going to get reversed in this thing. But if you want, you can put like n/2 swap gates at the end to get them back into your favorite order. OK. So. OK, so to do the 0th wire, we're going to try to go like, describe the computation like qubit by qubit. So we're just going to try to get the top qubit into this state. OK, and then I'll talk about getting the second qubit into this state, the third qubit into this state, fourth qubit into this state. OK, so first one, we're trying to get the top qubit into this state. OK, and as I said, we need to get, we want the top qubit to look like, well, it's up there. 0 plus omega bar to the 8x 1 over root 2, this state. Now, it looks like kind of a drag because this x is then still a number between 0 and 15. It's determined by these 4 input qubits. And it looks like we need to know capital X in order to figure out what state to get this wire into. But actually, we don't. Somebody see why? Yeah?
You only care about x mod 2.
Yeah, exactly. So if you look at this, right, this is like omega bar to the 8. Remember, this is omega 16th to the minus 8. OK? This was omega bar. It's like a 16th root of unity. But its 8th power is actually minus 1. OK? Its 8th power is like a second root of unity. It's minus 1. So like, actually, this is literally equal to, well, now this is, therefore, omega bar to the 8x is minus 1 to the x. Okay? So this is a number between 0 and 15. But like, if you want to raise minus 1 to a number between 0 and 15, you don't really care what that number is. You just care if it's even or odd. So this is also like minus 1 to the least significant bit of x, x0. And so you actually, to affect this transformation, you actually only need to know x0, the first bit. So this is actually 0 plus minus 1 to the x0 times ket 1 over root 2. And perhaps that looks familiar to you. Can somebody tell me how to get this state onto this qubit?
Hadamard.
Yeah, Hadamard transform. This is right. This is literally Hadamard applied to x0. Either make it ket plus or ket minus, depending on whether x0 is 0 or 1. So great. So we can just put a Hadamard on this wire, and like we're kind of done for computing the first qubit. Now I'm going to put it at the end, and I'll tell you why. Okay, when it comes to computing the next qubit, we are going to need to like use like the original value of x0. We're going to need to know that. And so we're going to need to like kind of look into the original value of x0 to figure out what to do to get the second qubit. And then at the very end, we're like, OK, now we're done. We'll like Hadamard that and get this wire here. OK. So this is sort of a mess. OK. Go to here, I guess. So now we'll work on the quote-unquote first wire. I mean, it's really the second wire, but it's the wire indexed by 1. OK, so we're trying to get this qubit, the second wire in the picture, into this state. Okay, so we need to get this. Okay, this is not going to be as easy. We still have this worry, right, that like, okay, this phase that we need to get onto ket1 depends on the whole number x. But it doesn't really depend on the whole number x, right, for a similar reason. Omega bar to the 4x, well, that's omega bar to the 4th to the power of x. And what is omega bar to the 4th? Who's paying attention? Minus I, yeah. It's right, this omega bar. So the 4th, it's the 16th of the way around the circle. So 4th power of it is a quarter of the way around the circle this way, clockwise. So it's minus I. Actually, we don't really need to know what it is. The only thing we really need to know is that, you know, minus I to the x doesn't fully depend on x, right? It only depends on x mod 4. Because minus I to the 4 brings you back to 1. So this is minus I to x mod 4, if you will. In other words, it only depends on x0 and x1, the least two significant bits of x. And actually, another way you can, write this, which will be good for our future way of doing this. So we'll just write x in terms of its bits. This is omega bar to the 4, x0 plus 2x1 plus 4x2 plus 8x3. And now, like, 4 times 4 times x2 is 16x2. But omega bar to the 16 is 1. So, like, this kind of goes away. Omega bar to the 32 is 1. So this goes away. So it's really just this. Omega bar to the 4x0, well, times omega bar to the 8x1. And actually, as we saw before, omega bar to the 8 is negative 1. And this is also I suppose. But so this is negative I to the x0 times negative 1 to the x1. Okay. In the future, I'll stop remembering what this numerical value is and just remember it's omega bar to the 4. Great. So what that means is, like, in this wire, kind of you need ket1 to pick up a phase of minus 1 to the x1. And also, you need to pick up a phase of minus 1 to the x0. Now, you could get the minus 1 to the x1 part, and also the over root 2 business by Hadamarding on the second wire. I mean, well, quote unquote, first wire. Okay, if we just put a Hadamard on the second wire, which again I'm going to do at the back. Well, actually, wait a minute now. Let me get this not wrong. Let me do it. I want to do it a little bit over here. We'll see. Actually, it doesn't matter.
Oh, no, because it's reversible. All right. Yeah.
But the point is, once we just have the Hadamard on the second wire, forget about this. We'll kind of get into this state, because we'll get the over root 2, and we'll get this piece of omega bar to the 4x, and we'll just be missing this piece. Okay, so like sort of the last thing we need to do is potentially change the phase on ket1 by this amount. In other words, don't change the phase at all on ket1 if x0 is 0. And if x0 is 1, do change the phase on ket1 by minus I. Okay, so like what we need to do to get this last piece here, I'll say it again. To get this last factor into play, we kind of need to do like if x0 equals 0, nothing. If x0 equals 1, then put omega bar to the 4 phase on ket1. Or in other words, if you think about it, like x0, x1, like if it's 0, 0, 0, 1, this is x0, this is x1, 1, 0, do nothing. And if it's 1, 1, we need to map it to omega bar to the 4 times 1, 1. So this is super messy, but so what we really need to do here is a controlled omega bar to the 4 phase operation. Okay, so we need to do this, x0, x1. I'll draw it like this. Okay, so this is like some 2-qubit gate that I just invented. Okay, we never talked about this gate before, but it's a simple 2-qubit gate. It does this sort of controlled phase operation. I mean, we talked before about this controlled Z operation, which does exactly this, except it's, the phase in that case was just -1. And so now we're saying, okay, it's a similar thing. It's a controlled phase shift on x1, where the factor is this other complex number. Okay, so this is some new 2-qubit gate that we just assume that we can build. And we plug it in to our circuit. And we'll be taking care of the second wire. Okay, and now the top 2 qubits are good. Okay. Now I'll briefly show you the third wire, and then the fourth wire will be kind of obvious, and then we'll be done. That'll show you all n wires. Yeah, by the way, I should just say this new gate, if you like, it's the 4x4 unitary matrix that looks like this, 1, 1, 1, omega bar to the 4. Okay, that's a nice diagonal matrix where the diagonal entries are of magnitude 1, so it's unitary. Okay, so let's do one more to do wire number 2, i.e. the third wire. Okay, again, I erased what we need to get, but it's similar. Need to get ket 0 plus omega bar to the 2x, ket 1 over root 2. And again, we look at how this omega bar to the 2x really depends on x. So it's 2x0 plus 2x1, 4x2, 8x3. We remember, omega to the 16, it's just 1. So this part kind of goes away. So we get omega bar to the 2x0 times omega bar to the 4x1 times omega bar to the 8x2. This is just good old -1 to the x2. And so it's similar to before. We can get this phase plus the whole square root 2 business by putting a Hadamard here. And to get this phase, well, we're going to do a controlled omega bar to the 4 between x1 and x2. And to get this phase, we're going to be doing a tall, controlled omega bar squared between x0 and x2. And that'll get all the phases right. So this looks like this. And then this. Okay, that gets it all right. And then I'm not going to do the last wire, but you can guess, or you can just detect the pattern by pattern matching. The last step is this. Well, I'll check my notes. Actually, I didn't even have the notes, so I better do it myself. Oops. All right, ta-da. And that is the quantum circuit that affects the 4x4 discrete Fourier transform. So let me make 2 small comments, and then we're done. I mean, you can guess what the pattern is for general little n. And what is the total number of gates? Basically, yep. It's, 1 plus 2 plus 3 plus 4 plus ... plus n. So it's n plus 1 over 2. Which, as I said, it's about n squared over 2. But anyway, it's less than n squared, which is pretty good, right? And little n is the small number. And if you want to like throw in some swaps to like fix the order, then fine, put in another n over 2 gates. Let me say one last thing. Imagine you were like literally doing this in practice because you want to like factor some, run Shor's algorithm, factor some 1024-bit number. Well, little n might be 1,000. And then it's a little funny, right? Like this gate would be like a controlled omega bar, where omega bar is like a 2 to the 1,000th root of unity. That's implausible that you're going to like physically build that, right? Like, how do you do a phase shift? Like you put the photon through some like quartz slab or something, or like you fire a laser for a certain amount of time. But you're not going to build like a quartz slab that's 2 to the minus 1,000th centimeters thick. Or you're not going to fire a laser for like 2 to the minus 1,000 seconds. So you might question, like, OK, this is fine theoretically, but does this really correspond to reality? Like, could you actually make this gate? Well, no, you could not actually make this gate. I mean, not like literally accurately. But luckily, and this was first pointed out by Coppersmith, there's such a tiny phase. You might matter. Does it really make a difference? And it doesn't. Turns out, if you just delete all the gates that involve phase shifts by at most epsilon angle, then you will overall compute a matrix which is in some sense epsilon close to the discrete Fourier transform. And it's not hard to check that that means that like, if the theoretical algorithm factored large numbers in Shor's algorithm with certain probability, the like approximate one just loses an epsilon on that probability. Okay, so you can like take epsilon to be like 1% or something. And then like you can delete all the gates where this phase shift is like smaller than like 1% or something. And actually, that's actually good for a couple of reasons. First of all, OK, so it turns out if you want to get like the epsilon accurate version, you just like delete all these gates. And you actually only need n log n over epsilon gates. In practice, you would just like any like one of these controlled phase shifts where like this distance is more than like 20 wires, you would just delete it. And that would affect your calculations by like 1%. So although it only approximately computes the Fourier transform, that's actually fine for your application. And now actually you got a way better circuit. Like instead of n squared gates, it has like basically n log n gates. So in the class in the future, we'll just assume, we'll not worry about that. We'll assume we're in like theory land and you compute it exactly. But actually in practice, everything is fine and it's even better. OK, so next lecture I'll tell you about Simon's algorithm all over again, but modulo for integers mod n.